Good morning, this is Schweitzer, and we're going to give you some answers to a mathematical relationships between the mass of particles and how many actual particles you have. So in this situation, get a little bit thinner line here. All right, so keep in mind, again, a few things that I just point out here is that mass, okay, is deceiving. So how many actual number of particles you have is varying number of particles. I often would remark in class the old third grade joke, you have 1,000 pounds of feathers, you have 1,000 pounds of bricks, which one weighs more? And the answer is they weigh the same, but you have a whole heck of a lot of feathers and you may only have one brick. So So in mass to number of particles, it doesn't, you don't know. All right, so I'll say if you have 1,000 pounds of people, how many people do you have? Well, you could have varying number, okay? Anyway, so we need to know inherently how much one particular substance weighs. So how much does a particular atom weigh? Well, in this situation, the nucleus is where all the mass is located, protons and neutrons. And for our periodic table, we have what's called an average molecular weight. So let's say, for example, let's go with helium. Helium is about 4.0. Now that's AMUs per atom. Okay, that means from this we're getting 2 AMUs due to protons and 2 AMUs due to neutrons. Protons and neutrons. Now this number varies, so we're getting on average about 4.00. This thing is really common to be just 2 and 2. Either way, this is AMUs per atom. Now that's a mass per particle ratio. Well, Avogadro's number, which is let's put it over here, which is going to be 6.022 e to the 23rd, was picked with an absolutely remarkable intuition, so that this 4.0 AMUs per atom also equals 4.00 grams per mole. So on the periodic table, the average molecular weight is equivalent to the AMUs per atom, but also the mass per number of particles. That's 4.00 grams per 6.022 e to the 23rd atoms. So if you divide these two, you'd have, into the simplest ratio, you'd have the grams per one atom. That's the mass of one atom. Okay, so again, it's just a relationship between how much a particle's mass is, or how much it weighs, to how many particles you have. And that's an important distinction in chemistry. So I can move this thing down here. There we go. Now there is just a ton of problems here, and I am absolutely not going to do all of them. And I probably would suggest you don't do all of them either. If you get once you get the idea, you practice a little bit, then you're good to go. So the mass of 1 mole is commonly referred to as the molar mass. Molar mass. Mass of 1 mole. If you did molar volume, that'd be for a gas, typically. It's the volume of 1 mole. So this is just the average atomic weight, which is what we find on the periodic table, or the molecular weight. Okay. All right. So this guy here. Now again, I might round some, just so you know. I'm not too interested in exactly all the decimals all the time. If it's really close, I just round it. But on the periodic table, so let's do a couple of these here. This guy is going to be 14 is the 0.01 is the molecular weight of this thing, and there's 2 of them. Okay, so all I do is multiply times 2, and my relationship is 28 is what I would typically do, grams per mole. Okay. Now how I will do this guy? This guy's a little bit bigger. Okay, so C6H12O6. All right. Now the only difference between molecular weight and molar mass is one is AMU per mole, AMU per atom or molecule, another one is grams per mole. So they are identical other than how they think of it. So this guy's molecular weight is 12 times 6. This guy's going to be 1 times 12. And then this guy's going to be 16 times 6. And again, doing all the math, you're going to get, add everything up, multiply everything up, is 180 grams per mole. Again, this is just a relationship. It's like saying you're going 80 miles per hour. How far did you travel? Well, you didn't travel. It's a relationship. If I have 180 grams per mole for glucose, how much glucose do you have? You don't have any glucose. If you had 1 mole, it would weigh 180 grams. If you had half a mole, it would weigh 90 grams. Okay. All right, so an example, let's say right here. This is the last example I'll do. Now, electrons here don't have a whole lot of mass, so we just ignore that. Here we go for this one. Again, how do I deal with these parentheses? Okay, well, either way, that just means you have 3 of these, 3 of these, and 3 of these. So I have 1 aluminum, which is going to be 27 for the aluminum. And then we have the hydrogens, which are going to be 3 of them. 1 times 3 is 3. And the carbon is going to be 12, 24, 36 for the carbon. And then the oxygen is 16 times 4 is 48. And you add those up for all your individual weights. And this will give you your the total molecular weight or the molar mass. 27 plus 3 plus 36 plus 48 is 114. So this guy here is 114 grams per mole. And I always like to put the units on there because it reminds me what this thing actually does. All right, so next one, number 15. Okay, so in this situation here, so I can just roll out a little more here. All right, and we'll only do a couple of these here, but it's more than just doing the mathematical relationships. So here, let's go with oxygen. Okay, I got 64 grams of oxygen. Keep my pen back here. Very good. All right, so now I have 64 grams of oxygen. The question here is, how many moles do I have? Okay, I don't know how many moles I have. Again, this is all about mathematical relationships. What I do know about oxygen is that 1 mole, okay, is equivalent to 32 grams. That's the molecular weight. Okay, that's a relationship that I do know. And of course, you can use straight proportions if you would like to do that. Factor label is just another form of proportions. So the way I run this is going to be, all right, is going to be 64 grams, dot line, get rid of grams, and go to moles. Now this is my relationship. 1 mole, this is my molecular weight, molar mass, 32 grams. 1 mole, you should be able to estimate this in your head. 1 mole is 32 grams. 2 moles is, again, I got that by adding that up. 16 plus 16 is 32. 2 moles weighs 64, 3 moles weighs 3 times that, so this divided is just going to be 2 moles. All right, next one here. Let's do number 19. First thing, sodium chloride is NaCl. All right, this is going to be 34.5. This one is, actually, that's the chlorine. NaCl, add up the molecular weights of this thing, and you're going to get 58 grams per mole. Now that's my relationship. So I only have 12 grams. So do I have more or less than 1 mole? Well, I have less than 58, so I have less than 1 mole. A half a mole is about 26, 27 grams, 28 grams, somewhere around there. Cut that in half. 50 would be 25, so 29 grams. So 29 grams is half a mole. I have less than that. And of course, this is about a quarter of a mole, because that's about a quarter of one of those. It's just estimating. Let's do the actual math here. So I have less than half, almost less than a quarter, 12 grams, dot line, grams, moles. 1 mole is equivalent to 58. And of course, if we do the math on this thing, divide it out, we're going to get 0.2. I have 3 sig figs here, so I'm going to hold 3 sig figs in the end. 0.206 moles. Okay? We've gone to the bottom. Now again, I'm going to go the other way. I'm going to just take, using fairly true, the grams. Okay, so I have 1.5 moles of water. First thing I need is how much water's molecular weight is, or molar mass. Oxygen is 16, 2 for hydrogen, 1 each, is 18 grams per mole. That's the tool that I need. All right, so 1.5 moles. Again, 1 mole weighs 18. I have more than 1 mole, so I have more than 18. 2 moles weighs 36. I don't have that, so my number's going to be less than 36. Dot line, get rid of moles. That particular thought process is super important. 1 mole is 18, and 1.5 times 18 is going to be the exact answer. The calculator will give me the exact answer, 1.5, and you can probably do this in your head too. Times 18, it's 18 plus a half of 18, which is 27. All right. And now the last thing here is that I'm going to do one example of the last one here. Now they want me to go from mass to number of particles. So I'm going to go from mass, and I'm going to plug this over to moles, and then I'm going to plug it over to number of particles. This is going to use the molar mass. This is going to use Avogadro's number. All right, so here we go. I have 90.5 grams, dot line, get rid of grams, and go to moles. That's my molar mass. Get rid of moles, and go to atoms. This is 1 mole is equivalent to 24.3 grams. That's the inherent weight of these particles. Now, a mole is equivalent to 6.022 e to the 23rd. Squeeze that in there. And my answer is 2.24, holding 3 sig figs, 2.24 e to the 24th. So this is a pretty common pathway. Be aware of that. Obviously I don't have a relationship that goes from mass directly to number of particles. I must go via moles. Okay. Thank you very much.